Hello, everybody. I am Dr. Karatim. I am an assistant professor in the Department of Civil and Environmental Engineering. Today, we're going to learn about the mass balance. So, mass balance is a fundamental concept we use every day, actually, in our daily life. As a student, for example, you have maybe some the financial aid, right? And then you have some spending, you have some income, and then you have some the outcome. Basically, it's just going to you are spending the money for the books and other things, and then you have the some maybe savings in your the bank account. So all these things actually it's related to mass balance. We do this kind of the material balance and mass balance in our daily life. Let me share my screen quickly, and we'll see some of the examples from the environmental engineering and during the daily life too, as I mentioned. So just give me a second. Um, what we're gonna learn today, we're going to learn the mass balance. The goal is to define the mass balance, the boundary, a pollutant of interest to establish the mass balance equation. And second, we're going to look at the mass balance in the different the conditions, such as the steady state, the conservative and non-conservative systems. And then finally, we're going to look at some of the systems, whether this system is steady or the non-steady system. So, okay, the mass balance is the law of the conservation of mass. When chemical reaction takes place, the matter is neither created nor destroyed. As you can see here, the one of the first step is the having this control volume or the control boundary into the system. And then let's see whether I can get my pointer too. And we have some inputs and we have some outputs, as I mentioned before. I give an example for your maybe the financial aid, the kind of the economic conditions. We have some inputs and then we have some spendings. And then we have some the control volume. We have some savings, which can refer to the accumulation. We can have some decay. We might be losing some money during the interest and other things. Interest refers to actually generation. Decay can refer to some other things, some extra spendings you have. So overall, the most of the systems, what we have some inputs, we have some outputs, and inside the system can be some reaction, such as the decay or the generation. Okay, so the mass balance is actually applied in the brewing, the making the beers. Here is actually at Florida Gulf Coast University, the students they make their own beer, and I hope you taste it. It's a really great the taste of the beer. It's amazing. They have this ability, but during this process, actually, they do use the mass balance, such as we have the inputs in this brewing process and we have some outputs. And then we can have the system or control volume around this whole process or specifically sometimes in some specific process too. So another example from the wastewater treatment. This is the wastewater treatment starts with the raw sewage, the water, and it goes to some of the physical processes such as the screening, and then after that goes to the primary sedimentation tank, and then some of the biological treatment in the aeration tank, and then secondary sedimentation. We do some chlorination, and we can discharge this water to the rivers. So this is the main the wastewater treatment, the processes. If you take the fundamentals of environmental engineering, you will see that you are going to see this each process is more learn about the details actually. So, but if you look at specifically here, the primary sedimentation tank, for example, we are talking about the mass balance. We have some inputs after the screening, removing the big particles, and then after during the sedimentation, gravitational settling, some of the particles settle, right? And then we have some output. And during this sedimentation process, there might be some reaction, and there might be some of the accumulation too. Another example on the natural ecosystem, such as this time is the water circle. In this process, we have this blue, the arrows, and then green arrows. Blue shows that the transfer of the water from atmosphere to the ground. Green is the reverse way, which is from ground to the atmosphere. So we have some input, we have some output, and also we have some reaction going on. Here, some of the crops can remove this water, and there can be some of the reactions. So all these processes actually is an example of the mass balance, which is really amazing. So we have the nutrient system, which is nitrogen cycle, which is similar to. We have some inputs, and then we have some output, the back to the atmosphere. But during this process, we do have also some of the bacteria, as you can see here in the nitrogen fixing bacteria, or the turning the nitrogen in a different form of the nitrogen, or decomposers, right? So there is a reaction too. And during this process, of course, there might be some of the accumulation into the soil, into the system too. So what we have here, overall, the equation is, if you want to write down mathematically, as an engineer, we do like to use all the time the equations and numbers. So what we have, the accumulation rate equals the input rate. We have some input to the system, and we have some output from the system, and we have some reaction going on. So the one example here, especially in Southwest Florida, we do have this algae blooms, which is a big problem. Still happens rarely after the 2016, but the 2016 was one of the worst time for this kind of the harmful algal blooms. So what happened in this one is the algae is naturally inside in the ocean actually, but needs to have the nutrients to grow and then to reach to this level. So there is some, of course, the farms and urbans using the fertilizers, which is nutrient based, that can leach into the ocean, and it's kind of the food for the bacteria. And the harmful algal bloom, the use to this and produce to this toxins. And in order to prevent this, in order to minimize this, there is a project from the U.S. Army Corps Engineering. As you can see, we have some input in here, and then we have some outputs all the way. So this is an example for the mass balance. So the understanding the nutrient flow and then minimizing the nutrient flow through the waters comes from the mass balance equation actually. So as you can see, we have some inputs, we have some outputs, two sides is the output. We do have this kind of examples in the environmental engineering for the pollutants too. So this is an interesting report. I would recommend you, if you have a time during the summer, please go ahead and check it out. So in addition, as I said, the environmental engineering, we do have a lot of examples related to mass balance, such as the oil spill. So with the oil, the one drop of oil actually has like millions of the different chemicals, which is really amazing, hydrocarbons. So during the oil spill, for example, the surface spill in this picture, as you can see, this dark black colors refers to oil. And there is going to be some of them is going to go to the atmosphere. Some of the light chemicals, light hydrocarbons, want to go to the atmosphere because they are really, really light. and some of the heavy hydrocarbons wants to go to the bottom in the ocean. They want to sink. So there is a distribution of these chemicals. So since we know the initial amount, the rate of the oil release, and we know the rate of oil in the water column, and the rate of oil is evaporating, and then the sum of the oil can be used by the microbes. This is a great food source actually for the microbes. It's a really high calorie the food. So the microbe loves this the oil. So they use as a food the carbon source basically. So we can write down the mass balance equation, very simple, and then we can find the accumulation rate, what's left over on the water. So exactly the same thing, we can do that on the beach too, because the oil particles, oil reaching the shoreline, it's really critical, and it has a huge impact on the creatures on the shore. So we can do the same example, the same idea, basically the same concept. We have some oils are evaporating, some of them is some hydrocarbons prefers to go to the bottom in the ocean or stick on the sand. We can write down the mass balance and try to understand the impact or exposure of the oil to the people. Okay, so what else we can do? Where we can use this one is the indoor air pollutants too, actually. So indoor air pollutants such as the particulate matter, which is really small dust particles, are really the critical on human health. The one example here is representing the human hair versus coarse dust. It's a little bit larger particles, and then PM2.5, and then ultrafine particles. As you can see, all these particles can reach the section in our respiratory systems. The PM2.5, which is a particulate matter 2.5, this refers to the diameter of the particles are 2.5 or less. Ultrafine particles is 1 micrometer. We have the regulations for the PM2.5. We do not have any regulations for the PM1 or the 1 micrometer or less, because these are really hard to measure actually. Analytically, these are challenging. So as you can see, these particles, PM2.5, can reach all the way to almost the lung system. So it can really have the permanent damage in our respiratory system, which is really the critical. So we do expose to this kind of things during when we are doing the Thanksgiving Day, for example, right? Making the turkey, there is this short video. I would recommend to watch it. Let me see whether I can click that, and then we can watch here quickly together.
We see and experience particulate matter, or aerosol particles, all around us. Aerosol particles make up the smog we see in our morning commutes, the trails of smoke that rise out of our campfires, and the sea spray that fills the air after a wave crashes against the rock. They're at the center of each and every cloud droplet, and in puffs of smoke from cigarettes. But did you know that we also encounter aerosols indoors? We might not typically associate aerosols with indoor spaces, but many research studies have detected a variety of particles in the indoor environment. So where do indoor aerosols come from? Maybe the most obvious source is when outdoor aerosols travel indoors. Air enters our homes and other buildings through doors, windows, ventilation systems, and leaks and cracks in the building envelope. The closer a building is to major outdoor aerosol sources, like busy roads with lots of traffic, the more particles end up inside. Some aerosol particles have indoor sources as well. A few examples of indoor activities that can generate particles are burning incense, lighting candles, or any other form of combustion really, as well as using office products like printers and 3D printers. But one of the most important indoor aerosol sources is your kitchen. Roasting a chicken, preparing a stir fry, and other cooking activities generate a large amount of particles indoors, especially when using a gas stove or oven. With so many surfaces inside, like the floors, walls, furniture, and carpet, particles are lost more quickly indoors than they would be outdoors because they stick to surfaces or settle due to gravity. But the particles we see inside, especially those generated from human activities like cooking, have the opportunity to influence our indoor air quality, and they can potentially react further, changing the chemistry of the indoor environment. Researchers are still working to understand their role in indoor chemistry and human health. To limit your exposure to aerosols, ventilate your kitchen while cooking. Look at websites like airnow.gov to learn more about outdoor air quality before opening windows. And reconsider your habits when it comes to burning candles and other activities that can affect your indoor air quality.
Using some of the floor and other things as the input, and we have some output, and also this particulate matter can have some reaction in the air too. So this is an example for the mass balance too. So as you can see here, we have similar as that, like we have some flow rate with the Q, we have the concentration, we have the control volume inside the house, we have some emissions, we can have some of the particles can sink, or they can settle easily, specifically the big particles. This is the settling, the Stokes law, and also we have some output, right? We can some of the chemicals, some of the particles can leave the control volume or our house. So overall, what the equation is similar as I shown before, accumulation rate equal to we have some input minus output and plus minus the reaction. Okay, so another example is this is the largest methane leak in California, Aliso Canyon, the air pollutant example. So, and this was a huge case during that time. That's one of the example again that there is an input to the air, the methane emission, and during this time, some of the methane can travel very far, and there is a lifetime for the methane in the atmosphere. And after that time, it's going to be turned to other chemicals. So we have some input, and we have some with the specific control volume. We can have the output, and then methane also reacts with the other chemicals. So as you can see, we had these chemicals, such as the methane, the air pollutants. They have a really negatively impact on the human health too. There is the short video. Please go ahead, click this link if you have a time, and watch, or the Google, the Aliso Canyon, the methane leak on YouTube. You will see the video, which is really interesting actually. So okay, the overall what we are talking here, there's a steady state and non-steady state system. So a steady state system, there is no accumulation rate. And generally, this is solved using the simple algebra. The no accumulation rate, accumulation is, we are talking about the mass balance, mass change per time. And then this is the mass per time, right, the unit. And this refers to concentration times volume, which is concentration mass per volume, and times the volume, you have the mass, again you have per time, equals to 0. And the non-steady state conditions, there's no equilibrium, and accumulation rate this time is not equal to 0. And for this kind of solving these equations, we need to use the integration. Okay, another important, the concept is conservative or non-conservative substances. Conservative substance, as the name implies, it doesn't change. It just stays as it is. There is no reaction occurring, no decay, no generation, which is the reaction rate is zero. So remember one more time is our mass balance equation, accumulation rate equals to input rate minus output rate plus minus reaction rate. So if the system is a steady state, you have the accumulation is zero. And if there is a conservative substance, your reaction rate is equals to zero. So the non-conservative, that time is that there is a reaction, and then for the reactions can be the zero, first or second order. In this class, we are not going to talk about this in detail. And just to know that if there is a decay, that means the minus. If there is a generation, production of something, then that's the plus. Okay, so the steady state conservative system, as we talked, we have the accumulation since the steady state zero and conservative reaction equals to zero. So we're going to write down this, the equation. We have the control volume and we have the stream, such as the river, for example. You can think about, we have the concentration of this substance and then flow rate of the stream. And then the waste, there is the waste discharge to this river. The concentration of this specific chemical on the waste, and the flow rate of the waste is the QW. Okay, so there is basically the two inputs to the system, and there is the output as a mixture. So as we talked, we have the accumulation rate is zero and the reaction rate is zero. This makes our job is easier. So if you write down basically what we are saying, input is equals to output rate. So overall, what we have, we are writing the mass balance again. Pay attention to units always. So we have the mass per time here, and mass per time on the other side. So stream, the concentration times flow rate for the waste, concentration times flow rate, and then we have the mixture. So, okay, so how about if we have the steady state with a non-conservative substance or pollutants? So this is going to be, this time there's going to be the reaction. Since we have the steady state, accumulation rate is zero. The reaction rate again can be the positive or negative, depends on that compound or that specific case, can be the generation or decay. Okay, batch systems with a non-conservative substance. The batch system means that there is no inflow or no outflow. This is an example for the complete mixed, the batch reactor system, for example. And what we have here, the accumulation rate equals the input rate minus output rate plus minus the reaction rate again, the mass balance equation. But there is no inflow, there is no outflow. So what we have is the accumulation rate equals to reaction rate. So you might be wondering why I do have this washing machine, the picture here, because this is a great example for the batch reactor. So we do not have any input, right? What we do, we throw the clothes inside of this washing machine, and then we fill up with the water, with the detergent we are adding, and then what happens inside the detergent, the surfactants, mostly they react with this oily part of this clothes and clean the clothes. Basically, we do take out remove the greasy things or particles, and we do have the clean the clothes at the end. So this is an example. There is no input, there is no output, but at the end we have some reaction going on inside the reactor. And this is the complete mix too, because it mixes during that time. So as I said before, these are the complete mixing, the homogeneous distribution assumed. This is generally called a completely mixed batch reaction. Some of the examples are bacterial concentration in a closed water tank, or the concentration of the CO2 in a poorly ventilated room. Yeah, you might come up with the different examples. Please let me know if you have some interesting example for the batch system. So okay, so we're going to talk about the activity next. So the activity is going to be applying the mass balance model to explore the atmospheric carbon dioxide over the past 40 years and emission rates and emission growth rate. So during this activity, you are going to look at some of the atmospheric carbon dioxide data, and then you are going to try to understand, explore this data, try to understand and expect or calculate for future emissions. So we're going to talk about that soon. So all right, talk to you later. Thank you so much.